So welcome everybody to our Gamma seminar. Today we have the pleasure to guest Henrique Bursztyn from the IMPA, who will talk about Lie groupoids and Poisson geometry. So Henrique, thank you very much for accepting our invitation. It's a pleasure to have you here. And the floor is yours. Please go ahead. Thank you.
Okay, well, let me start by thanking you for the invitation. It's a pleasure. I'm particularly thrilled to talk to an audience. At least half of the audience would not have a problem to spell my last name, and that's something very unique to me. So the talk is really a basic talk about Lie groupoids, highlighting their connections with Poisson geometry and related geometries. And this was somewhat on demand. Not last year, I think in 23, I posted a paper for the Encyclopedia of Mathematical Physics with Matias Del Hoyo about Lie groupoids, and to a large extent, the talk will be based on this paper. I'm taking some stuff from that paper. I certainly cannot cover everything, or not nearly everything that is mentioned there, but that's the idea. So the central character of the story, are Lie groupoids. This is a notion that goes back to the work of Ehresmann in the 50s. And there are many natural ways that one is led to study Lie groupoids. It's really it offers a very general framework to study several known objects in geometry in particular. So here are some examples. Lie groupoids naturally arise from group actions, from foliations, from pseudogroups, from principal bundles, and I'll be highlighting how they arise in connection with Poisson geometry. And the nice thing about having this common framework is that we can often adapt ideas, from one of these fields. Once phrased in terms of Lie groupoids, they are adaptable to the others, right? So you can transfer ideas from different areas in a way once you have a common framework. And another interesting aspect of Lie groupoids that I will not be talking about today, in principle, is that they also give rise to very interesting objects. So, for example, in the study of certain singular spaces and moduli spaces, one often uses the language of stacks, and Lie groupoids are behind them. They are a very rich source of C-star algebras. They can give you like a bridge from geometrical structures to non-commutative algebras, which is the basis of non-commutative geometry. They give rise to certain simplicial manifolds, and you can use simplicial techniques to study Lie groupoids, and therefore all these objects that give rise to them. And they are also part of a very interesting Lie type theory that generalizes the connection, the very well-known connection between Lie algebras and Lie groups. This will also play a role here today.
Henrique.
So here's a brief outline. I'll start just telling you what a Lie groupoid is, list a bunch of key examples, and then pass to their infinitesimal counterparts, called the Lie algebroids, and list a bunch of key examples, say a little bit about how they are related by Lie theory, and then tell you how these things connect with Poisson structures and related objects. Okay, so that's the general plan. So before giving you like the formal definition of a Lie groupoid, that it's simple after you understand it, but I think that if the first time you are seeing it, it could be a bit overwhelming. Let me start with an example. So one approach to Lie groupoids is that they are generalization of groups. So let me start with a very simple group that I think we have all encountered. So if you have a manifold and you fix a point in this manifold, one defines the fundamental group, right? It's an important topological invariant. which is basically consists of homotopy classes of paths that start and end at the point that you chose, and you can concatenate them, and you take homotopy classes to make this associative, right? So this really becomes a group, and something that we study a lot, and we try to compute this in various examples. What one could try to do is get rid of the choice of this point x, and really just talk about paths on M, homotopy classes of paths with fixed endpoints. But now, they don't have to be based on any given point. If you do that, then in general, you will not be able to compose them, to concatenate them. But you can, if the two paths satisfy a certain condition, which is that, the end point of one is the initial point of the other, right? So upon this additional condition, you can still concatenate. So basically, the difference between these two objects is that here you can compose any two elements that you want, and here you can't. You just have a partial multiplication. You can only compose if a certain condition is satisfied. So this is like a prototypical example of a Lie groupoid. So let me try to formalize that. Okay, so a Lie groupoid, and this will be my notation, consists of two manifolds that I'm calling G and M. For reasons that will be evident later, we usually refer to elements of G as arrows and elements of M as objects. Okay, and then you have two surjective submersions from G to M, right? And in terms of a picture, one thinks of elements of G as an arrow that relates its source, which is an element of M, to its target, which is another element of M, right? And this multiplication-like structure that we'll put here will be defined in terms of these two surjective submersions. So for that, I will define this fibered product here of G with itself over M, which consists of pairs of elements in G, denoting them by H and G, subject to the condition that the source, which is this S map, it's called source of H, matches the T map, the target of G. So that's the condition, right? And this is a nice smooth manifold, again, because these maps were taken to be submersions, right? And, this space is where the multiplication will be defined. Okay, so the first structural map that is basically the main map of the groupoid is really this multiplication, right? Which is a map from this set of composable arrows, right? So the source of one matches the target of the other, satisfying this condition that, so given a G and an H, with a matching condition, you have a new element that I'm denoting here by HG. And the S map, the source of this map, is the same as the source of G, and the target is the same as the target of H. Okay, and this map is associative whenever it makes sense. So if you take the product of three elements, then, if you can compose them in whatever order you want, this should agree. There's a second structural map here, which is the unit map. So the manifold of objects, M, it sits inside G through an embedding, through a map that I'm denoting here by epsilon, is the unit map, with the property that to each point X of M, one associates an arrow that begins and ends at X, okay? And this arrow really serves as a unit in this sense, right? So whenever you can multiply, a unit by a certain element, you just get the element again. Okay, but you have different units on the left and on the right because you need the composition rule to be satisfied. And there is a third structural map here, which is the inversion, which has the property, basically, the source and the target of the arrows are reversed. And when you compose, an element with inverse, you get the corresponding unit. Okay, the unit that makes sense. So these are the properties, the defining properties of a Lie groupoid. So a pair of manifolds, two surjective submersions that allow you to talk about, a certain, subset of the direct product, which I will call composable. On this subset, I have a multiplication, and then I have units and an inversion. So let's try to recognize this on this example of
Henrique?
Yes.
Sorry, yes, a little question. Which
Yeah.
was the original reason to start studying Lie groupoids? I mean, like groupoids, yeah, because with the Lie is just the differential structure, and the initial one maybe was with manifolds, was more general, yeah?
Yeah,
Differential.
I think one of the motivating examples was the fundamental groupoid. And Ehresmann himself in geometry, I think, was, if I'm not mistaken, motivated by the theory of principal bundles. So I will try to explain the connection a little bit, but
Okay.
it came from there. Okay, so let's try to recognize these maps or this structure on the previous example. So in this previous example, I will take as the manifold G exactly the so-called fundamental groupoid. So the collection of all homotopy classes of paths on M. This turns out to have a natural smooth structure, so it's a manifold. And the source and target maps are just the evaluation of this path in the beginning, at the initial point, and at the end point. So I'm taking paths from the interval 0, 1 to M. Okay. And, the composition condition is that, therefore, this guy here is, given by the pair of paths, so that, the initial point of one matches the end point of the other. And in that case, I can just concatenate them, and that's my partial multiplication. This unit map is a map that allows you to see points of M as paths, right? So if you give me a point of M, I can just associate to it the path that doesn't leave that point, right? Just a constant path. And you know that if you concatenate a path with a constant path, then you just get the same path again. And inversion is just reparametrizing the path, changing the direction. Okay. Good. So that's our first example, the fundamental groupoid. So it showcases all these features. So the simplest examples, I started with an example that showcases some of the structural maps, but the simplest examples are cases in which the manifold of objects is trivial, it's just a point. Then we're just talking about a Lie group. And the other case, the other extreme case, is when the arrows are trivial. And these are just manifolds. So in this case, G equals to M. The source and target are the identity map. And the multiplication is just the obvious thing. You can just multiply a point in M by itself, and the result is itself. Okay, it's very trivial. But that's the way one sees a manifold as a particular case of a Lie groupoid. And this is the way one sees a Lie group as a particular case of a Lie groupoid. Right? When M is a point, this condition for pairs to be composable is vacuous. So you can compose any two. And as you would expect, there's a natural notion of morphism between Lie groupoids, which is just maps that preserve all the structural maps, and of subobjects, of Lie subgroupoids. I think no one would have a problem to figure out what they are. okay? And from, the algebraic object underlying a Lie groupoid, for those more algebraically minded, is that of a category. So you can imagine, that's a bit, the terminology comes from that. You can imagine that algebraically, what you have is a category G with set of objects M, with the property that all arrows in the category are invertible. That's what distinguishes a Lie groupoid from a general category. And I'm doing everything in the smooth case here. Okay, so groupoids have a couple of very important ingredients. One of them is for given any point of the groupoid, there's an orbit associated to it. And this orbit is defined by all the elements in M for which there is an arrow on the groupoid G that has source X and target that point Y, right? Or so the formal definition is this. Or put differently, a groupoid establishes an equivalence relation in M, which is, 2 points are related if there is an arrow that goes from one to the other, right? And the orbits are the equivalence classes. And in the case of a Lie groupoid, they turn out to be, it's a little theorem proposition, they turn out to be submanifolds, immersed, not necessarily embedded submanifolds. Once you fix a point X, one can also look at all the arrows that start and end at that point. And this is a group, right? Among those arrows here, I can compose them, without a problem. And this turns out to be a Lie group. And just to give you a picture, pictorially, what's happening is that, if you have a Lie groupoid, right? So M is a manifold. One way to see or to smell that there is a Lie groupoid around is that M acquires, a partition into submanifolds, the orbits, and to each point there's an associated Lie group around, right? And one is often interested in the orbit space of the groupoid, right? Which may or may not be smooth, but often one studies groupoids interested in this, in the orbit space. And there's another thing that I want to mention is that there's a very nice way to put together, to relate the orbit and the isotropy group, which is the following. Because the source maps the submersion, its fibers are all submanifolds of G, right? And, you see by the definitions here that, the source fiber of X has a natural action of the isotropy group at that point. You can naturally compose these two things, right? And this turns this source fibers into principal bundles over the orbits. So you really have a family of principal bundles associated to a groupoid. Okay, so they have a very rich internal structure. Okay, but the picture to have in mind is this: is that you have a decomposition of M into submanifolds. It's a kind of it's a singular foliation. Singular here meaning everything is smooth, but just to say that the dimension of this submanifolds, they don't have to be constant, right? Much in the same way that you decompose a manifold when you have a group acting by orbits, and the orbits don't have to have the same dimension. Okay, so it's a type of foliation. Yes.
Just one question, because you can't talk about groupoids, Lie groupoids, by means of theory of categories, as you said. But yes, it's a general question whether, in your experience do you think that this approach gives something more powerful than the geometric approach? Because I'm curious, because I always studied this from the geometrical point of view. I was interested in geometrical aspects. I know that there is a categorical way of understanding this, but I don't know if it's useful for something, or even I don't.
Yeah, I mean, it could be useful. So, for example, one thing that is typical to categories is that um, you know you don't really consider two categories. So you could say that two categories are isomorphic, right? So you have functors going in one way and the other way, and when you compose them, you get the identity. So
Yeah.
they're just isomorphic. You could define that, but that's not useful for categories, right? Usually in categories, you have a notion of equivalence that is weaker than that, because there is a natural notion of map between functors. So usually you define two categories to be equivalent, right? If the composition, so you have a functor, you have another one, and the composition is equivalent to the identity, not equal to the identity.
Yeah.
What this means is that in a category, really what you want to retain from the category is not just all the objects, but the set of isomorphism classes of objects, right? And yeah, so in the same way, so from this perspective, if you have this in mind, if you have this categorical idea of groupoids, you see that the natural notion of equivalence between groupoids will be more along these lines. What you want to retain from a groupoid, in a way, is the orbit space, right? Which is the collection of isomorphism classes, and the automorphisms of the objects. That's exactly what an equivalence of categories retains.
Oh, okay. Yeah.
Right. So what I'm saying is that if you want to define, so if you're interested in a space which you realize as the quotient of a groupoid by its orbits, there are many different groupoids that may look very different that you would like to identify as giving rise to the same thing.
Yeah, I understand the point. Yeah.
Right. So I think for the notion of morphisms between groupoids, maybe the categorical approach would make that more natural. I don't know, but it's good to have that viewpoint.
Yeah, it's sure. And I understand, for example, in cases in which you have certain class of groupoids with a certain structure common to all of them, to maybe could be interesting. Okay, thank you, Henrique.
Okay, so that's pictorially what you should have in mind.
A related question, this categorical approach. One can define a Lie group as a group object in the category of smooth manifolds. And this gives a natural way to generalize to the notion of Lie supergroup and so on and so forth. So is there like some way to define like that Lie groupoids?
Yeah, I think it's the same way. So I could define algebraically a groupoid as being a category, or better, people to be super strict, a small category, because we're talking about sets here. So in which all the morphisms all the arrows are invertible. So that's the summary of my definition of a groupoid. And you could talk about groupoids internal to smooth manifolds, right? I mean, a groupoid object in smooth manifolds, and those would be Lie groupoids, in the same way that you just defined the Lie group.
Okay.
So you could talk about groupoid objects in topological spaces, and those would be topological groupoids. Or you have groupoids in schemes, and you have groupoids. You can talk about a groupoid object in a category, and talk about different types of groupoids.
Okay, thanks.
Yeah. Anyway, so let's just, for concreteness, let's identify, these isotropy groups and the orbits in our favorite example, which is the fundamental groupoid. So for the fundamental groupoid, the isotropies, right? So you fix a point and you take all the arrows that start and end at that point. So the isotropy groups are exactly the fundamental groups based at different points, right? So these are these guys here in the case of a fundamental groupoid. And the orbits are, so two points are in the same orbit if there is a path linking them. So we are talking about the connected components of M. So these are the orbits. And, this principal bundle that I was talking about in this case also acquires a very known, something very known, which is the fact that, in the case of the fundamental groupoid, the source fiber, let's suppose that M is connected for simplicity, but the source fibers, so these are all the paths, all the homotopy classes of paths that start at a point that you chose. So this is exactly a model for the universal covering of the space of M. And we know that on the universal covering, there's a natural principal action of the fundamental group at that point, right? And the orbit space is M itself, right? So that's the principal bundle, or the family of principal bundles that we would have in this case, right? One for each point X. Anyway, but we can recognize now this structure in several examples. Let me just list a couple here. So a slight simplification of the fundamental groupoid is the so-called pair groupoid. So basically, you keep track to what happens, with the endpoints of these paths here, right? So an element of the pair groupoid, so this is just like the product of a manifold with itself. So it's just a pair, and you can compose them. So the projection, the first component is the source. The projection to the second component is the target, right? And you can only compose them if they are in this situation here. So the target of this is the source of this, and then you delete this guy, right? That's like what happens with the endpoints of the paths when you concatenate them, right? So this is a simplification because it has no isotropies. So we have, on this direct product, you have exactly one arrow between any two points in M. A variation of that, a generalization somehow, is if you have a submersion. So if you have a submersion from M to N, you could now only take pairs that project to the same point on N, right? So this is a subset, a submanifold of M cross M, and there you do the same kind of composition. And what you get here is that the orbits of this submersion groupoid are exactly the fibers of this map, right? And the orbit space is exactly the base N, the counter domain N. Right. Maybe I should, I won't use this, but just to say that there is a very special case of this construction, which attaches in a natural way a Lie groupoid to any open cover of M. Right. We take the disjoint union of the cover. This is a manifold again. There's a natural submersion onto M. Right. And if you carry out this construction, you get a groupoid in which the arrows are double intersections of the opens in this cover. This turns out to be very relevant for many constructions. So another example to mention is the action groupoid. So here you just have a good old action of a Lie group on a manifold, and then you take as your groupoid the direct product of the group and M, right? So now elements are pairs, X in M and G in G. And the source is just X, and the target, which must be a point in M, is just G operating on X, right? And this has a very natural groupoid structure that codifies the group structure of G and the action at the same time. Right, so here it's easy to see that the orbits of the groupoid, of the action groupoid, are just the orbits of the action, And the isotropy groups, as I defined, are just the stabilizers of the action, right? So usually we use this notation for the action groupoid. And another interesting example is the analog of the general linear group of a vector space, right? So whenever you have a vector space, you can consider all the group of linear automorphisms of this vector space, and that's a Lie group, right? Now, if instead of a vector space, you have a vector bundle, I'm denoting by E, then you can attach to it the general linear groupoid. And here, an arrow between X and Y is a linear isomorphism from the fiber over X to the fiber over Y, right? So this groupoid only has one orbit, right? So I call them transitive. And you see that the isotropy groups of this groupoid at a point, these are exactly the general linear groups of the fibers, right? So the linear automorphisms of the fibers.
Henrique?
Yes.
There's one question that came to my mind now.
Mm-hmm.
You can describe the flow of a vector field, not complete, okay? A general vector field by means of a groupoid.
Yes.
Maybe, yeah?
Yeah.
I mean, the so-called also local Lie groups, you know, that, for example, you have a Lie algebra vector fields, but they're complete, and you have some kind of, it's not a group really, yeah? Because you cannot construct it. It's like a Lie group close to the neutral element. You can describe it also by means of groupoid, yeah? Something like that.
Yes. So there is a notion, so two things. So there is a notion of a local groupoid in which the multiplication is only defined if you're close enough to the identity, to the units. That's one thing. And the other, so this example that you gave, that's interesting. I did not include it here, but it's interesting. So indeed, if you have a flow, right, a flow of a complete vector field, right, it's nothing but an action by R.
Yeah,
right? So you could associate an action groupoid to that. Now, if the vector field is not complete, right, you could still take the, like the maximal open subset, the maximal domain where the flow is defined, right, as an open set of R times M. And there you have an honest groupoid structure. It's not even a local groupoid. It's actually a Lie groupoid.
Right.
It's
because, for physicists, normally it's the stuff you get. Sometimes physicists, they assume that everything works fine, vector fields are complete and things of the sort to define the structures. But I was lately taking a look that by means of groupoid, certain even easier stuff appearing in physics where vector fields are not complete and things like that, maybe they could somehow be addressed by means of this stuff. And there are even basic problems that they have technical issues and they are not studied normally by means of these techniques. And it could be interesting. Thank you.
I think it's a very it is a very convenient thing. So, flows of not necessarily complete vector fields, give rise to groupoids as well. So there are many more examples to mention, but for the interest of time, I won't mention many more. But there are groupoids naturally associated with principal bundles. Much in the same way that you associate this groupoid to a vector bundle. You could take for a principal bundle as arrows maps between the fibers of the principal bundle, which are G invariant, which are equivariant with respect to the action on the fibers. Then this would be a groupoid. It's called the gauge groupoid of the principal bundle. And this was one of the initial motivating examples, going back to your question in the very beginning. So this groupoid only has one orbit, so it's transitive. And for a long time, in fact, the only groupoids that were studied were transitive because they were equivalent to principal bundles. Only later that people relaxed this condition and started to care about the orbit structure that you have on M. And as a last example on this list, just to tell you that you have groupoids associated in a natural way with foliations. So here you can take, for example, a version of the fundamental groupoid in which you only allow paths to be contained in leaves of the foliation, right? And then you concatenate them in the same way, but now, the paths, they always respect the leaves. And this is called the monodromy groupoid of the foliation. And it's another important example and the orbits are, of course, the leaves. So you can realize the leaves of any foliation as orbits of a Lie groupoid, if you want. Right. And, you can talk about, there are many functorial constructions involving groupoids, taking the tangent bundle, taking the cotangent bundle, and these are all groupoids again. And these are very interesting objects, which are, if you want, vector bundles in the world or in the category of groupoids, right? So you have here, this is a vector bundle over G, this is a vector bundle over M, and, the left-hand side is a groupoid over the right-hand side, and these two structures interact in a nice way.
And sorry, Henrique, other structures and other ideas from differential geometry can be generalized. For example, in the cotangent to a Lie groupoid, you have some kind of symplectic groupoid, yeah?
Yeah.
Oh.
Yeah, exactly. So I'll get to that. Yeah, that's a good point. Exactly.
Right. Thank you. It would be great.
Yeah. Okay, so there's a lot more to be said. If you go to the survey paper that I mentioned in the beginning as my source of inspiration here, you'll see lots of other aspects of groupoid theory, of Lie groupoid theory being developed. So one of them is, for example, representations, right? Once you know what the general linear groupoid of a vector bundle is, and that's a groupoid, you can talk about groupoid morphisms from any given Lie groupoid to that. And what does that mean, right? So it means that you are realizing an arrow of an abstract groupoid as a linear isomorphism between fibers of a given vector bundle, right? In the same way that the representation of a Lie group is the realization of an element of the Lie group as an automorphism of a vector space. And what is interesting here is that this thing acquires a lot of geometrical meaning. So you won't have trouble to see, for example, that a representation of the fundamental groupoid of a manifold is the same on a certain vector bundle. So what am I saying here? So you're taking a path and attaching to this path a linear isomorphism between fibers of the corresponding, of the corresponding fibers here over these points, right? So basically, you are lifting a path on M to a linear transformation on the fibers, right? And so that's parallel transport, right? It's like something that is related to the presence of a connection on the vector bundle. And the fact that, it's a representation of the fundamental groupoid says that, this linear transformation is independent of the homotopy class of the path, which says that this connection is flat, right? So a representation of the fundamental groupoid on a vector space is the same thing as a flat connection. And a representation of the pair groupoid is the same thing as a trivialization of that vector bundle, a flat connection of that vector bundle, I'm sorry, right? So representations are extremely interesting objects that generalize the theory of connections, for example. And you can talk about, just like I just mentioned, the action of a Lie group on a manifold. You can also have a theory of actions of Lie groupoids on manifolds. But now Lie groupoids don't act only on manifolds. You need a map from the manifold to the base here to the units of the groupoid. And what the groupoid does is that it relates the fibers of this map, just like it related the fibers of the vector bundle here. So going back to the, also to a question from the beginning, from this categorical perspective, it becomes evident that the notion of isomorphism of groupoids is too strong. So there's a weaker notion that is called Morita equivalence that is explained in this survey paper, that basically is the notion of equivalence that retains exactly the information about the orbit spaces and the isotropy groups. So it's something that looks at the transverse geometry to the orbits, right? You can have very different actions and orbits that have the same transverse geometry. And what's captured by this notion of equivalence, Morita equivalence, is exactly that. Okay, so from this perspective, from this weaker perspective, for example, any groupoid with only one orbit is equivalent, is the same as a Lie group. Okay, so it's something very, very important. And there's all kinds of differential geometric questions that one can pose and study and answer for Lie groupoids. For example, how they look like around orbits. If you have you may have linear models, whether you can linearize the groupoid around the orbit. And these are all related to classical questions for group actions and for foliations and, things like that. So you can kind of unify, many of these theorems about models around orbits or leaves in the context of Lie groupoids. Okay, so let me briefly mention the infinitesimal counterpart of a Lie groupoid. So these are called Lie algebroids. So the connection is similar to the connection between Lie algebras and Lie groups. But now a Lie algebroid, instead of a vector space in which you have a Lie bracket, you have a vector bundle in which you have a Lie bracket on the space of sections. And you have an additional ingredient here, which is called the anchor map, which is a map from A to the tangent bundle. So basically it anchors, that's what the name suggests, like something that happens on A to M, right? And there is a Leibniz rule that must be satisfied. And the general features of a Lie algebroid is that, the kernel of this anchor map is always a Lie algebra. And the image of this anchor map, so what it gives you is that it gives you like a subspace of the tangent space at each point, something that we tend to call a distribution in geometry. Even though here I'm not taking really a subbundle because, as I said, the rank can vary from point to point. But nevertheless, this distribution, this generalized distribution, is integrable. So you always decompose, M, the base of the vector bundle, into leaves if you have a Lie algebroid over it. Okay, so the structure is similar to that of a Lie group, of a Lie groupoid, I'm sorry. So you have leaves, but now instead of attaching a Lie group to any given point, you have a Lie algebra attached to any given point. And there's a natural construction that takes a Lie groupoid to a Lie algebroid, which defines the so-called Lie functor that extends the Lie functor from Lie groups to Lie algebras, right? And the construction, is fairly similar. So basically, on a Lie groupoid, you take as the vector bundle the normal bundle to this submanifold M. Remember that M sits inside G as the units. So you take the normal bundle of that, and you use the source and target maps to create the anchor and you define the Lie bracket on sections of A by identifying sections of A with invariant vector fields on the groupoid. So it's very much in the same spirit, of what you do for Lie groups with the necessary adaptations. Okay, so examples of Lie algebroids. So a Lie algebroid over a point, right? The vector bundle becomes a vector space, and you just have a Lie algebra in that case. And the other extreme case is that for any manifold, you can just take the vector bundle with 0 rank, and that's trivially a Lie algebroid. A less trivial example is the tangent bundle of a manifold. So in this case, you take the anchor map to be the identity, and the Lie bracket on sections of the algebroid, sections are just vector fields. That's the usual bracket of vector fields. And it turns out that this is exactly the Lie algebroid of the pair groupoid or of the fundamental groupoid. You have two different groupoids that lead to the same Lie algebroid, in the same way that you can have different Lie groups that have the same Lie algebra. So if instead of the whole TM, you just take an involutive subbundle, a subbundle whose sections are closed under the Lie bracket, this is also a Lie algebroid in a natural way. And these are the Lie algebroids of these groupoids associated with foliations. Infinitesimal actions also give rise to Lie algebroids, and these are the Lie algebroids coming from group actions, so on and so forth. Right, so there are many other examples. So I could talk about the general linear algebroid of a vector bundle and things like that. Okay, so I can't really, time flies, and I haven't even gotten to Poisson manifolds yet. So let me just mention two things. Is that the usual classical theorems of Lie theory, they have versions here that hold, right? So one thing is that if you have a Lie algebroid that is the Lie algebroid of a certain groupoid, this is also the Lie algebroid of another groupoid that you can choose having simply connected source fibers. So that's the analog of the fact that you can always pass from a Lie group to a simply connected Lie group without changing the Lie algebra, right? Just an analog of that. And you also have the ability to integrate morphisms from Lie algebras to Lie groups, as long as in the counter domain you get this special one that has source simply connected fibers. What goes wrong here is the fact that, as opposed to what happens with finite dimensional Lie algebras, not every Lie algebroid can be realized as the Lie algebroid of a Lie groupoid, right? So this was something not completely understood for many, many years, until by now, many years ago, Kreinig and Fernandez described in generality the obstructions, what prevents a Lie algebroid from being integrable, and gave various examples of Lie algebroids that are and are not integrable.
Enrique,
in light of yes.
That was an Annals of Mathematics, yeah?
Paper. Yes. Yeah. That was a very influential paper. It's a classic by now in the Annals of Mathematics from more than 20 years ago. But it's a paper where they describe precisely the obstructions for a Lie algebroid to be integrable in terms of the discreteness of certain subgroups. Anyway, it's a long story that I wouldn't dare to.
I see. Just a comment. When I was before even I was a PhD student, I knew that result that came up. Everyone was amazed by it. Now it's fun that everyone considers it a classic. Yeah.
Yeah. Well, right. It kind of became a classic, and it's not. It was not easy. It's not an easy result. It involves technicalities, but it has been revisited from different angles. But it's something that I think it's fairly well understood now. Yeah, but you're right. It was something that everyone was kind of surprised when it came out.
Thank
you. Now, so if I have 10 minutes or 5 minutes, I will just briefly mention how this connects with Poisson geometry. So, just a brief recall of what a Poisson bracket is on a manifold. So just a Lie bracket on the algebra smooth functions that is a derivation on each entry. And there's a classical fact that any Lie algebra gives rise to a linear Poisson structure on its dual. Like by linear, I mean that it's a bracket that preserves the linear functions, which are just the elements of the Lie algebra themselves. So that's why I wrote this here. So there is a straightforward generalization of this fact, which is the first connection between Lie algebroids and Poisson structures, which is the fact that more generally, any Lie algebroid gives rise to a Poisson structure on its dual. Now, the Poisson structure is defined on the manifold, that is the total space of the dual bundle. But now, instead of only caring about linear functions, right, which are sections of A, linear functions on A star, you also have to care about how linear functions on A star interact with functions that come from the base M. And that's where you use the anchor. Right. And a very, very simple example of this duality between the algebroids and linear Poisson brackets is the fact that, one of the simplest examples of a Lie algebroid, as I said, is the tangent bundle of a manifold, where the bracket is the Lie bracket of vector fields. If you dualize it, you get the cotangent bundle. And the Poisson structure, the linear Poisson structure there that corresponds to this bracket is precisely the canonical one. Okay, so the canonical symplectic or Poisson structure on the cotangent bundle is as canonical and in fact dual to the Lie bracket of vector fields in this sense. The second way in which Lie algebroids and Poisson structures connect is a bit more interesting. It is the fact that any Poisson structure gives rise to a Lie algebroid structure on its cotangent bundle. So you take as A the cotangent bundle of M as the anchor, the map induced by the Poisson structure from the cotangent to the tangent bundle. And the bracket on the sections, which are one forms, they're naturally induced by the Poisson bracket in this way. That's all you need to know. And then in this case, the leaves of the symplectic groupoids are the so-called symplectic leaves of the Poisson structure. And the isotropies, which are these Lie algebras that you attach to each point, they are the Lie algebras dual to the linear approximations of the transverse Poisson structures, for those who know what they are. And, I described two ways that connect Lie algebroids with Poisson structures. One starts from a Lie algebroid and dualizes it and gives you a special type of linear Poisson bracket. And the other one starts with any Poisson manifold whatsoever and constructs a Lie algebroid on its cotangent bundle. So the relationship between these two constructions is not that one is the inverse of the other at all, but if you start with a Poisson manifold and you pass to its Lie algebroid, right, and you dualize it, now you are on the tangent bundle of M, not on M anymore, and you get a Poisson structure there dual to the Lie algebroid that was induced from this one. And this process is known as the tangent lift. It's a natural way to promote a Poisson structure on M to a Poisson structure on the total space of its tangent bundle. And do I have 5 minutes or should I cut it short?
No, please go on. We are always late. It's not a problem. So take it easy.
Yeah, I don't want to steal too much of your time, but anyway.
It's okay. It's okay. Never mind.
So just to tell you that because associated to any Poisson manifold, I've told you that there is a Lie algebroid. You may wonder, okay, so moral of the story here is that a Poisson manifold, from this perspective, is an infinitesimal object, right? Because it's naturally associated with the Lie algebroid. So a natural question is, what is the global counterpart of a Poisson manifold? Now, how do you integrate it, or you integrate it to what? And that's where these objects known as symplectic groupoids come into play. So a symplectic groupoid is just a Lie groupoid, as I have previously defined, equipped with a symplectic structure on the total space here, on the space of arrows, with a compatibility between the symplectic structure and the groupoid structure, which can be summarized with the fact that the graph of the multiplication map sitting inside 3 copies of G is a Lagrangian submanifold. And the bar here is because I have to switch the sign of one of the symplectic structures. This can also be described by one single equation, which is this equation here. That if you consider this space of composable arrows, you have the multiplication and the natural projections. So if you pull back the symplectic form on G, the discomposable arrows, they have to satisfy this equation. Okay, so there's an equation that relates the groupoid multiplication and the symplectic form. And the two key theorems now, which involve a number of people like Alan Weinstein, Mackenzie, and Shu, and many other possibly, is the fact that if you start with a symplectic groupoid, right? So there's no Poisson structure around here on M. But if you start the symplectic groupoid, M canonically inherits a Poisson structure in such a way that the Lie algebroid of G is naturally identified with the cotangent Lie algebroid of this Poisson structure that M inherits. Okay, so any symplectic groupoid in this sense integrates a Poisson structure. And on the other hand, if you start with any Poisson manifold, and if you assume that its cotangent Lie algebroid can be integrated, and this is not always the case, then you can always find a groupoid integrating it that has canonically a symplectic form, that is canonically a symplectic groupoid, right? And the one that is canonically a symplectic groupoid is the integration that is source simply connected, the one with source fibers simply connected, this universal one.
Sorry, Henrique, one question. The cotangent is integrable. The condition to be integrable is a hard, very restrictive one, or just depends, or can you?
No, I mean, you can cook up examples as I will mention, but many natural classes of examples of Poisson manifolds are integrable.
Yeah.
On the other hand, it's not hard to modify integrable Poisson structures to make them non-integrable.
Okay, I understand.
So you can find simple examples which are not integrable, but many of the natural classes of examples are integrable.
Okay, thank you. That's what I wanted to know.
So let me mention 3 prototypical examples of symplectic groupoids. So if you take a symplectic manifold, and if you consider the pair groupoid associated with this manifold, this is a symplectic groupoid. And it in fact integrates the symplectic manifold itself in this sense. So the groupoid integrating this Poisson manifold that is very special is the pair groupoid, or can be taken to be the pair groupoid. So we know that any cotangent bundle has a canonical symplectic structure. And this can be seen as a symplectic groupoid, where the groupoid structure is just fiber-wise addition. So you take the source and target maps to be equal, to be just the natural projection from the cotangent bundle to M. So you can only multiply elements if they are over the same fiber of the cotangent bundle, and the multiplication is just addition, right? So in this sense, any cotangent bundle is a very, very simple example of a symplectic groupoid. And the Poisson structure it induces on the base is the trivial one, right? It couldn't be anything non-trivial because there's no canonical Poisson structure on a given manifold, right? Except for the 0 one. And in a similar way, you can always see cotangent bundles of Lie groups with its canonical symplectic forms now in a different way as a groupoid, now as an action groupoid, where the groupoid acts on the dual of the Lie algebra by the coadjoint action. So this is a symplectic groupoid integrating the linear Poisson structure on the dual of any Lie algebra. And as pointed out before, the cotangent bundle of any Lie groupoid is a symplectic groupoid that integrates the Poisson structure on the dual of its Lie algebra. So this is a general fact. And there are several other, as I mentioned, there are many other, so, it's an important problem that is much studied to describe or to know if natural classes of examples of Poisson manifolds are integrable and describing their symplectic groupoids, right? So for example, Poisson Lie groups are known to be always integrable, right? And it's nice because you can even construct symplectic groupoids which are simultaneously symplectic groupoids for the Poisson Lie group and for its dual. So, it's the same symplectic structure, but this symplectic manifold has two groupoid structures. One that sees the Poisson Lie group and the other one that sees the dual Poisson Lie group, if you know about this duality in Poisson Lie group theory. So this is actually an example of a double symplectic groupoid. And in a recent paper, I think it was only published last year, with David Iglesias and Zhang-Huan Lu, we proved, and we extended this fact, and we proved that any Poisson homogeneous space is integrable, and we described their symplectic groupoids. So just to finish, I just want to mention that there are many reasons to care about symplectic groupoids, and just to briefly say some of them. So as I said, groupoids are interesting or rich sources of C-star algebras. So if you can attach a groupoid to a Poisson manifold, you should be able to attach a C-star algebra to a Poisson manifold. And that's what quantization is about. So there's a program that was first laid out by Alan Weinstein, with further input by Eli Hawkins, that in a way formalizes this. It's a construction that is difficult to carry out in practice, but in theory there is a way that by means of symplectic groupoids you can associate C-star algebras to Poisson manifolds. So these objects, for those more into physics, symplectic groupoids, they also arise in a very natural way from certain topological field theories, from the so-called Poisson sigma model, as the classical phase space of the sigma model. So this is a topological field theory in which the target is a Poisson manifold, right? And you have a certain action that uses the Poisson structure on the target. And so if you figure out what the classical phase space of the sigma model is, you'll find the symplectic groupoid. And they give a way to vastly generalize the theory of Hamiltonian actions, where now you have, instead of Lie group acting, you have symplectic groupoids acting. So this notion of Morita equivalence can be adapted to Poisson manifolds and turns out to be very important. And in recent years, symplectic groupoids really became an indispensable tool for results in Poisson geometry, like calculation of Poisson cohomology, for example, or showing that certain Poisson cohomologies vanish, and in this way proving certain linearization results about Poisson structures. So they turned out to be very, very useful. So here's just my summary. It's just that I didn't really have time to talk about what happens beyond Poisson manifolds, but there's like this very vast generalization of Lie theory that starts from Lie groups and goes to the algebras back and forth. And you can view Lie algebras as particular Poisson manifolds by means of their duals, right? And you can see Lie groups as particular cases of symplectic groupoids by means of the cotangent bundles. And you have a generalization of classical Lie theory to this level. And these are all part of this Lie theory that I mentioned about Lie groupoids and Lie algebroids. And there is an intermediate layer that I won't have time to talk about. But I heard that you heard about Dirac manifolds. And also in a paper from 2003 that I wrote with Kreinig, Weinstein, and Zhu, we identified the global counterparts of Dirac manifolds, and they turned out to be very, very important as well. For example, to describe the geometrical structures behind quasi-Hamiltonian spaces and group-valued moment maps, which were designed to explain the symplectic nature, for example, of the moduli space of flat connections, which is very important in physics, in Chern-Simons theory, for example. And these are all like very, very simple examples, these quasi-symplectic groupoids of what is now called shifted symplectic geometry. So these are like one-shifted symplectic groupoids. So I'll just finish here. Sorry for taking more time.
It's been a pleasure. Thank you. Let us thank the speaker. It's been a pleasure, Henrique. Your talk was very clear, really very interesting, and for students and also for us to see that the final review of hot topics, so to say, the last years. So, okay, is there any question, remark, comment?
I have a comment.
Yes.
Okay. So there is an application of groupoids to continuum mechanics. In continuum mechanics, the mechanical behavior is described by a constitutive law. Using this constitutive law, you can identify a family of so-called material isomorphisms. There are certainly linear isomorphisms from the different tangent spaces at different points on the body, and this is
right.
This is the material groupoid.
The material groupoid, yes, I remember
Yes,
those.
and you can study the uniformity of the material using this groupoid, and even for the homogeneity of the body, you can use this. In this case, you have a Lie groupoid, and you can characterize the homogeneity using the Lie groupoid. Even more, probably will be appear tomorrow a paper by myself and Victor Jimenez and Marcelo Esten about the application of double groupoids to study composites, composite materials. The materials composed by two different materials.
Oh, wow. I'm looking forward to that.
So this is the right way to study this material thing, just using double groupoids.
Oh, that's very good to know. We like to find applications of those.
Yes.
And yeah, but that's a very good point. Of course, I didn't mention, there are countless applications of group, even like they appear even like in numerical treatments.
Yes.
In the development of numerical methods for in geometric mechanics. And yeah, I mean, the list is way too long. So what I mentioned here, like this, small connection between symplectic groupoids and Poisson geometry is just the tip of the iceberg. It's one of these things that once you know about them, you find them everywhere.
Sure.
So yeah, thank you. Yeah, that's a very good point.
Thank you for the talk. Very interesting.
Oh, thank you.
Okay. Is there any other question?
Just a quick question. What about contact groupoids? I mean, how much they are developed in comparison with symplectic ones?
Yeah, so I think they are a bit less developed. Yeah, so that's a very good point too. So yeah, I could just go on and on, but yeah, so there is a yeah, so there is like the odd dimensional version of symplectic groupoids, known as contact groupoids, and the infinitesimal geometry related to them, or encoded by them, is that of Jacobi structures, right? Which is the kind of contact analog of Poisson structures. So everything kind of matches, and yeah, and they turn out to be very useful too. And they actually turn out to be useful, even if you don't care so much about Jacobi manifolds, but only Poisson manifolds. You know, if you integrate a Poisson manifold, you know, as a Jacobi manifold, you find a different object, something that is not quite the symplectic groupoid. It's going to be a contact groupoid, and and sometimes these guys they have nicer properties than the symplectic groupoid itself. So yeah, there's a lot going on in that direction as well. But I would say that they're not as studied or as developed yet.
Okay, thank you.
Any other question?
Well, related with the previous question, I know that a PhD student of Luca Vitagliano called Antonio Maglio, he finished his
That's
thesis.
right.
He
Yeah,
did it about precisely contact structures on stacks.
that's right. Yeah, that is correct. Yeah, by chance, I was in the PhD thesis committee, so I happened to know what you're talking about. Yeah, so Maglio wrote a thesis about this contact groupoids, but as I mentioned in the very end, you know, like the the more general perspective to the symplectic groupoids now are in terms of this shifted symplectic geometry. So it places them in a much more in a much broader and general framework. And yeah, so what he did was to study this one shifted contact structures, which turned out to be basically these contact groupoids. Yeah, but from this broader perspective. Yeah, that's right.
I had to write a center bar report about that paper lately too.
Uh-huh. Yeah, yeah.
Okay.
So there is yeah, I think Vitagliano is really the person who has been pushing this contact groupoid Jacobi story
Yeah.
more.
Okay, is there any other question, remark? No, so thank you very much, Henrique.
Well, thank you for the invitation, and thanks for all the questions. It's always good to, you know, exchange ideas like this.
Yeah, sure. It's been really nice, and you have a nice way of explaining and very clear, and it also shows maybe new perspectives. Thank you, Henrique. So,
All right.
well,
All right.
everybody, and see you in a week.